All right, it's several minutes after the hour, so let's get started. Okay. Okay, my name's Ron Block, and a little bit about my history. I don't know where to begin. Let me say it this way. Has anybody heard of Polyphaser? Okay. That was a company formed by my brother 50 years ago, almost. And he was the one who decided really to go make the coaxial protector. Before that, nothing like that existed. And it was driven by a case of he had a project that he was building, and he happened to be working in Kissimmee, Florida for an antenna manufacturer. And so he took the project, finished it. They had to go up on the roof, connect it up to an antenna to test it. And they, made some progress. Some things weren't working and whatnot. So he left it there and comes back the next day to a pile of cinders, because it's Florida, Kissimmee area is the lightning capital of the U.S. So the antennas were struck and killed his project. So we had to recover from that. He did. About a week later, went back upstairs, didn't learn from his mistake, did exactly the same thing, made some progress, left for the evening, comes back the next morning, pile of dust. So he said, I got to do something about this. It's happened twice in a row. Well, that's the founding story of Polyphaser Corp. And it's interesting, having lived through that, my children have lived through that. It wasn't until, maybe a year ago, all of a sudden, I recognized my brother started the lightning protection industry for electronics and coaxially connected equipment. Before that, it just didn't exist. So, a little bit of background. He taught me well, I hope. All right, I thought we'd start with a little bit of the characteristics of the process. The thunderstorm that we were hoping to avoid today, we did, so that part's good. Our thunder protectors are working. However, we did have some rain. And if we look at the overall process, especially the pictured there is basically an anvil cloud, which is some of the most dangerous. And that little spark that comes down from the sky is about 6 miles long on average. So that's quite a voltage difference. And it delivers about 30,000 amps on average. Now, off on the right-hand side, you see the range. It's from 3 to 140,000. So it's got quite a range. And that's only about 98%. There's still another 2% that are not in those numbers. So we're not worried about the low end so much as that 140 could be 500 or 1,000, which is, 1 million amps. It's always possible. The pulse rise time is very interesting. The average for the first strike is about 1.8 microseconds. And if you do the simple 1 over it, then you'll find out that that's 555 kilohertz. That's RF. So not only is there a tremendous amount of DC component to it, there is an RF component, and we have to treat it as if it's an RF component, because that's the harder one to handle. It's interesting, I'm doing some research, hopefully thinking about publishing a book on this whole process, at least document what I know so somebody else can make some benefit from it. I just learned that the second strike actually has a much faster rise time. Instead of about 1.8 mics on average, it's about 1/10 of a microsecond. So you do 1/10 over 1, or 1 over a tenth, and you find out that you've got some real RF here. You're up in the megahertz of the range. So that's important stuff. Okay, the average thing, just so as you look at lightning, you see that it sort of flickers a bit. Well, that's because there's multiple strikes. And the average is 2 to 3, and the range goes all the way out to about 12. Okay, so that's a quick overview of what that stuff looks like. Now, how we came about this. Now, the club members that are here, of course, know this, but we have a club member, John Hill, who was able to be a benefactor from Mr. Sterling and actually give the club a full power, 1.5 kilowatt linear amplifier. The only requirement is that it had to have a ground. The operative word is a ground, or just one ground. Well, as we looked at the situation, this is sort of an aerial view of the club, you find that the red circled items are independent grounds. We have several towers. Each one of those, of course, is grounded. The AC itself is grounded. And all of a sudden, we find that we have 6 grounds. Now, one of the problems with multiple grounds is that if you just look at this as, there's a tower ground and a utility ground, and of course, utility comes with its own set of ground rods. The tower, of course, is going to set with its own ground rods. Now, if we take a strike on that tower, get the mouse to work here, we'll find out that the energy as it dissipates into the earth begins to expand, like ripples on a pond. Okay? Now, what happens if we stop that sort of midstream is that if we connect a radio to the tower, because it's got an antenna on it, and we plug it in to the AC, guess what? We are bridging those 2 grounds. If that tower takes a strike, there's going to be a significant voltage difference between the tower ground and the AC ground. Okay? The AC ground in this picture doesn't know it's coming. It does take a finite period of time, and in many cases, just so I don't confuse the world with some of my words, we're talking about nanoseconds or low number of microseconds. So I mean, it's not a long time, but having damage occur to a radio takes but a couple of hundred nanoseconds. So the damage occurs very quickly. Okay, so here's that classic radio, just connected to the tower, which has its antenna, and plugged in. And you find out that it is now the equalizer between the 2 ground potentials. And of course, as it spreads out, the potential becomes less. But before it spreads out, potential is very significant. Okay, now, the same picture here, except this is your house. Okay, you see the antenna on the left, the utility ground on the right, both of which the grounds are indicated by green, the blue coax cable coming down from the tower, and the radiacy power protector. So if you take a strike on the tower, then the energy comes and follows that, goes through the radio, and then back into the AC, which is still lower potential, and into the utility ground system. Okay. Everybody comfortable with that? Who has that connection? Yeah, I did in the beginning too, so don't. There's a solution, and it's not a bad solution. Okay. If you would take the time and add what has a long word, single point ground panel, okay? That's a simple thing. It's a chunk of conductive surface, copper, aluminum, tin. I don't think steel is recommended because it's going to rust, and rust on a dry day is not conductive, so that's not good. But it's a conductive metal surface, any size, any shape. Despite the fact we're going to see it here as a nice, neat rectangle in green, it can be anything we want. It can be a copper pipe, which also works. On that single point ground panel, we mount a protector, one coax protector, developed by my brother to protect his experiments when he was building stuff for the antenna manufacturer. Okay. The second protector that's on there is an AC power protector. Okay. Those 2 cables, the coax and the AC power, are the only external connections for that radio. So it's very easy to identify them. Okay. Now what happens is that the energy comes down the tower, goes to that single point ground panel, and then proceeds into the ground on the utility. Not necessarily the best case, but because the energy flows through the structure, but it will protect the radios. Okay. Now how it does that, I think, yes, the next slide. How it does that is kind of simple. A coaxial protector, when you overvoltage it or when you threaten it with an overvoltage, does a simple thing. It just shorts the center pin to the shield, or in this case, to the case of the protector. Okay. That's easy. Now, on the AC power, if you overvoltage it, it will short the hot and the neutral to the case, which is grounded. So now that will short circuit. If you mount them on a conductive surface, now you have the radio as if it were a doorknob, because all of the wires that are connecting it to the outside world are all shorted together. That's a key point. Everybody's comfortable with that? Go ahead.
Where should it be located?
That's a tough question, and I'll tell you why. When I wrote the article for QST over a year ago now, right after it got published, I had probably a dozen and a half emails, hey, can you help me here, or what about this, or what about that? But 5 independent questions were, where shall I put my single point ground panel? So I wrote another article. And about 2 weeks ago, I got a note from Matty Weinberg up at ARRL saying, we're going to put you in QEX. That's kind of the wrong audience. I mean, I'm a QEX subscriber, but I don't think it's the right audience. However, we're negotiating, okay, because I'm also thinking about writing a book, and that will be one of my chapters. So we have to figure out who owns what, when, and how. To answer the question, there's 3 choices. The most ideal choice, and probably the hardest to implement, is through the wall. I think I have a slide on it. Look at that. It happens to be next. Through the wall. That is, you cut a hole in the wall of your house, and you put a piece of metal plate in there. Okay, that conductive surface, that single point ground panel. You mount your protectors from the inside, and if you use the right protectors, they actually protrude through the plate so that you can put your coax in on the outside. Okay, you can run a connection from the surface of the plate that's outside into the ground. So there's your ground connection. You can run another piece of conductive material to bond all your chassis to. So, I mean, it's a great thing. The only problem is that we live in an environment where the temperature and the humidity vary widely, and you'll go from ice to water to ice and more water, and structural damage. So that one doesn't work so well, but that's the ideal case. And I have seen it in a couple of hams. In fact, one of the gentlemen was just here last hour. He's probably my first friend that did that, and he still has it. It still works. I've seen it in commercial installations where they'll take the plate, but the plate will be the size of the garage door or the size of the entire wall as a metal plate, and all of the protectors will be mounted there. But this happened to be a building with about 200 transmitters in it, and towers, and you name it. So it can be done. It's not necessarily practical for home use. The second one is outside the shack. That one is a little bit difficult in that, yes, there are folks who sell adapter plates that you can put on the end of a ground rod, and you can mount your coaxial protectors on it. Okay? But as we've just seen, that's not enough. You must also protect the other external connection for your radio, which is the power. Now, if the power protector has inductance built into it, which is highly recommended and is the better way to do it, then you're going to have a voltage potential difference during the strike event between the power going into the power protector and the power coming out of the power protector. That means you cannot take the unprotected input cable and lay it up next to the protected output cable and expect to survive, because you can get a spark gap because of the voltage difference. So handling that in an external environment where you take the power out of the building to the ground stake where the power protector is, and then bring the cable back in, you've got to keep them separated, and of course you've got to protect the whole thing from weather. That's a bit difficult. So we back up into a third level of trade-off, and that is you put it in the shack. And generally you choose a spot along the logical flow from where the cables may enter to where the radio desk is. And you just pick a spot in the middle and chop the cables, put the single point ground panel on the wall, put the protectors on it, and it works. The disadvantage is that you're bringing the energy into the structure and then you're taking it back outside again. Now, there's exceptions and all kinds of deviations in this process, but I'll just mention one. Okay. What we're talking about so far are the primary protectors, the coaxial protector, the power protector, and if there's a rotor involved, a rotor protector. And of course, you can have multiple coaxes, and you can have multiple powers, especially if you got 110, 220, or whatnot. So, or have enough equipment to exceed the 15 amp or 20 amp rating, then you've got to have multiples for the given voltage. However, if the cable has to wander through the house a considerable distance, then we need a secondary set of protectors just for the coax to get the energy off the cable so it doesn't spark to the structure of the house. Now, an extreme case in point, a colleague had an old Victorian house on, I don't know, 20 acres or something like that with multiple towers. And so he's bringing hard line in. So he brought it in through the basement. About halfway across the basement floor, he went up to the third floor, okay, across the top of the third floor, down to the second floor, and then across a little bit more, and then down to the first floor in the opposite diagonal corner. Okay. That's an extreme case of thou shalt have a secondary set of protectors to get the energy off that cable so that it doesn't set the house on fire. Okay. So, but that's clearly a secondary case. So, did I answer your question? Yeah, I didn't give you a good answer, did I? I didn't say do this. No, there isn't. There isn't. It's all highly dependent upon your site. And, I'm happy to talk to you about it at any point.
Why is the energy in the cable inside the house if there's protectors on the wall going into the house?
I'm not quite sure I understood the question. Why?
You just said you have to protect the cable inside the house.
Yeah, you put a secondary set of protectors on it.
This is the first set of protectors protect the cable.
Okay. I didn't say something. Let's go back here. Okay. You see here the coaxial protector on the left and the power protector on the right. And when they get over voltage, they short circuit to their cases. Their cases are mounted on a conductive surface, so the radio, the three wires connecting to the radio, are all shorted together. Okay. That has to happen within a very short time period. Otherwise, you will get some current flow. So the need there is to keep the protectors relatively close to where the radios are. Now, electrons are moving, give or take, about a foot a nanosecond. And when you get up into the low 20s of nanoseconds, you're really exposing yourself to the beginnings of semi-permanent or transitory damage. You get up, into the 30s and 40s of nanoseconds, you're into potentially temporary damage, and you start getting higher into the 50s and hundreds of nanos, and you're into, it's dead. So you've got to keep these things co-located. So I think your question is then, what happens? Why can't that set in my friend's house as it enters the cable, or as the cables enter the house in the basement before they wander through? Sorry about that. The answer is they're too far away. Then the timing is off by too much. It's off by probably 1,000 or 2,000 nanoseconds. So you got to keep it local and close. Okay. Okay. Now we talked about one of the disadvantages of locating the single point ground panel in the radio room along the logical path of the cables, which is kind of what this one shows us. One of the things that I highly recommend you do is that, well, let me say it differently. If you stop and just put the single point ground panel in and do not ground the single point ground panel to an external ground, it will still protect the radio. The thing you run into is it's going to take a long time, in electron terms, for that energy to dissipate into the ground system. half a second, that's an eternity in, when you're looking at nanosecond world. So the logical thing to do and the performance and the safety thing to do is to ground that single point ground panel. So the next step is, of course, run a connection from the single point ground panel through the wall outside and put a ground rod or 2 or 3 or 4 or 5 into the ground and connect them. But you've got to make sure that that is not creating another independent ground. Okay, much the way we started the project at W2MMD, we had, a bunch of towers. We had 6 independent grounds. Okay, and I'll show you what we had to do to fix that. So you don't want to create one more. So then it's necessary when you have that, connect that panel to the outside world, that you tie in the tower ground, the utility ground, and the new single point ground panel ground. And the easiest way to do that is to take a bare wire and bury it in the ground and use it as a bonding connection. Everybody comfortable with that?
How wide does it have to be?
Now we get into the other parts of the trade-offs. You can get away with a number 6 bare or something like that. Whatever becomes available to you. However, the recommendation is that use 1.5 or 2 wide copper strap. Because remember, this is still RF. And RF on a number 6 is kind of reactive, to say the least. Water pipe, yeah, it has surface area. And that's a good thing, yes. Okay, let's go back to the MMD thing. Okay, on the right-hand side, you see what's labeled HF. That's our high-frequency room. And that's where this full 1.5 kW amplifier is installed. And what we did there is we took and created a single-point ground panel that was composed of a 6-inch piece of copper strap, and then we ran that about 3/4 of the way around the room. Of course, we omitted the doorway so you could get in and out without having to step over it, so that part worked pretty well. And then we connected that 6-inch wide copper strap with the frame and with the external ground using another piece of 6-inch copper strap. Okay, and then we just sandwiched them together. Okay, that gives us a beautiful, conductive, low inductive surface. Okay, we're planning to do the same thing on the VHF side. We'll run a copper strap around the room, in this case, actually into the 2 adjacent rooms, because one of them's a lab and the other is our security system. Okay, so here's a brief view of what the room looked like before it started. It was a paneled room, and the X's up above the green line represent where the electric used to be. Somebody, when they put this together, said, oh, yes, you're going to have a desk in front of that. You want to just reach up and plug in. That's great. But you can't do that, and I'll show you why. So the X's removed to the rectangles below, and then the green represents the single-point ground panel as it goes around the room, and then the 2 vertical green segments are the connection to the outside world. So it is a nice, clean, low inductive path. Now, about here, I usually take a departure and say, if you've got a simple radio station, maybe you don't have to remove all the equipment from the room and or reroute all the power. 1 or 2 radios, that probably is okay. But if you're an old timer and some of the station pieces have been around since, you were a kid, and they maybe still work, or at least they're plugged in and maybe have an antenna on them, I'd recommend taking everything down, emptying the room. You'll be surprised what you find, but after you recover from that shock, putting it back together is an important process because it gives you the opportunity to shorten the cables. I said, well, what's wrong with it? I'm running it from radio A to the one that's about 1.5 feet away, and I'm using a 30-foot piece of cord. No. Even if you wind it up nice and neat and tie wrap it and position it so that it's okay, it's still a secondary of a transformer. that nice wound coil. It's air wound in this case, but it's still a nice wound coil. And it's on the protected side of the house. And since it's on the protected side, it's going to pick up energy and induce it into the protected equipment. And that defeats your purpose. So it's a pain in the neck to put everything back that way, but it's necessary. In our case, too, we had Ethernet from the other side of the building. And since it was a considerable distance and way out of time for getting good protection, we converted that to a fiber link with a local adapter to give us the electrical side, and it works beautifully. Okay, here are some of the guys that did it, and we won't dwell on this, but you recognize some of them. A few are even in this room. All right, here's a shot. We mentioned that we have the connection to the outside world, and so here's the 6-inch copper strap coming viewed from the outside of the building, where it comes down and picks up the frame of the building, a steel frame, and then is in a trench. And let's see, the ground rod, I guess, has been driven, but it's not connected in this particular picture. So this gives us our connection to the outside world. Now, this is one of my favorite things. What this is going to show you as I'm going to pan around the room, and we should be able to see. There we go. We can see the single point ground panel, and we'll stop and look at these again. There's leaving the picture of the coaxial protectors. Coming in the middle of the picture is the AC power protector. You can see another one down a few feet down, and the copper strap continues around the room. Run that one more time for you. And as of 12 o'clock, by the way, you are invited to go up to the clubhouse. VE testing will be over, and you can see it for real. Okay, here's another shot that this is sort of in the middle of that picture, and a couple things that are worth pointing out here. One, does my mouse show up? Yes, it does. Okay, if you could see, that's an AC power protector. Okay, and you've noticed in the way it's installed, it comes from the bottom, which is this is where at the wall, this is where the AC comes in, goes through the protector, and then out to a long power strip. And all of them do that except for the 240 volt ones. Okay, that shows us or puts us in a position that the only way we can get power for any piece of equipment in the room is this protected power. There is no opportunity at all to get unprotected power. That means we can't plug something into the wrong place and still have it interconnected with the rest of the equipment and be bridged across protected and unprotected. That will kill equipment also. So that's important.
Where's the unprotected wire on there?
The unprotected part is from the wall outlet to the protector. Let me zip back to a slide that I skipped over a little bit of.
Point out that slide that shows the cable going out to the ground rod is misleading. It doesn't show depth. It looks like the copper is at the surface of the ground, but it's not. It's actually down in the trench.
That's true.
You can't see that in the photo.
That's true. Yeah, that cable, the 6-inch copper strap coming out of the building is down it's about a foot down. Okay. On this picture, I guess I neglected to point out, if you look at the single point ground panel in green, there's a dotted line that runs sort of through the middle. And it's labeled unprotected toward the top and, unprotected toward the bottom and protected toward the top. Okay. Everything below center in this picture is unprotected. The antenna line coming in and the AC power. Okay. Everything leaving the panel on the upper half of that picture is considered to be protected. And in the case of specifically the AC power, as I mentioned, one of the disadvantages of trying to put it outside on a stake with your coax protectors is that there is a spark gap potential between the protected side and the unprotected side on the AC power protector due to inductance. That's the inductors that are inside. Okay, they will cause a spark gap. So it's necessary to maintain a physical separation between protected, in this case on top, and unprotected on the bottom. Did I answer your question? Okay. And then over here, under the edge of the desk, that's a 240-volt AC protector. Okay. We put in these cable loops so that coax cables, as they're put in, or any of the cables, go through the loops before as they go to equipment, so that gravity doesn't pull the cables down. Here's an example of them in use. Okay, this particular picture shows from the left the rotor protector, which happens to be a custom-made series device. I also do manufacturing, so it's easy to make those things. Next to that are 4 coaxial protectors for the 4 antennas that are outside. And then the black box that is next to the right is an antenna switch. And that's got a controller that does all the switching automatically based on frequency. Okay. And then to the right of that, you see that yellow with the white outline to it, which is the AC coming in to a protector, which is behind the edge of the table. Okay. So that's a simple single-point ground for this radio station. And there's a picture of it before the amplifier arrived, and I haven't taken a picture of it since. But that's the basic station setup.
Why was there copper going straight up?
Good question. One of the things that you have to be careful about when we're handling huge energies, energy pulses and whatnot, is that the voltages will rise, and sometimes into the tens to, I won't say hundreds, but it'll go into the 50s and 60,000 on a bad day. And that has the potential to flash over to anything metallic, especially if it happens to be connected to a ground, because of timing disparity between the elevation, say, of the single-point ground panel and the frame of an air conditioner in the wall. So what those vertical pieces are tying in to metal objects that are nearby. Okay? When you run when you run the interconnect between the AC power, the tower, and your single-point ground panel, basically you should look at that area, look at it from the wire's perspective, 4 feet in all directions, to find out if there are any metal objects where a flashover could occur. And if that's possible, then you bond it to the ground. Okay, and we'll see where that's going to come into play. Okay, our next step, okay, is you see the HF room and you see its connectors, or its connection to the outside world. You see the HF room on the left, and it'll have 4 connections to the outside world. And now what we do to unify the ground system is run a thing called a perimeter ground around the whole building. Perimeter ground does a couple of things. First, and most importantly, it allows us to bond all the grounds together. So as you look at this, you see that we bond on the left the 2 6-inch copper straps that come out from the single-point ground panel. You see that it also bonds, as you look toward the middle on the upper side of it, it bonds to the propane tank that's sitting in the backyard. Okay, it bonds to a satellite tower. It bonds to the utility ground. Okay, as we continue around, you see on the VHF room, 2 of its conductors. In the middle of that's another antenna tower that's grounded that needs to be bonded to the system. And then, of course, it encompasses the building. Now, one of the reasons that you want it to encompass the building as you saw in one of the earliest slides, if you take a tower and you let it have a nice lightning strike, that energy is going to spread out. That spread out energy is going to take time. It is possible for, we have an HF tower sitting right up in here, right there. If that tower were struck, it's going to take time for that energy to spread. There will come a point in time where the HF end of the building is elevated by several thousands to tens of thousands of volts. The VHF side says, nice day. Nothing's happened. It's calm and peaceful. Of course, that's only going to last for, a couple of microseconds. But in the middle, the trailer or the building has the opportunity to help conduct that energy because it's better, it's more conductive than the earth is. So therefore, the energy will actually hop out of the ground and onto the building frame and follow any piece of metal on a good day, or wood, or construction materials that's non-conductive on a bad day, and the potential for fire and infiltration of the electrical and the mechanical systems is possible. So you don't want that to happen. So the second reason for the perimeter ground is to act as a shorting bar in the soil around the building. That way, that as the energy comes off of that tower, which is on the outside of the perimeter ground, the shorting bar now helps it equalize so that it goes around the building, not necessarily through it. It's a help. It's not a guarantee, but it works and it's very effective, and it keeps the building from participating in the conducting of the electricity. Okay, that's a key item for the perimeter ground. In addition, of course, to tying everybody together. Now, what happens once we get the perimeter ground in there to help alleviate the stress on the internal circuit protectors, the coaxial protector and the power protector? We want to put a set of radials on each of the towers and basically enhance that ground system substantially so that we actually run the potential of being able to get 70–80% of the energy to get into the ground before it begins to follow the coax cable into the building. And that's possible by adding radials. It also improves communications. You've got a good ground system at that point. That's about it. Here's some references if anybody is interested in following up. I will say I do make myself available. If anybody is seriously interested in putting in a good grounding system, I'm more than happy to look at the plans and things like this. I will ask you to do certain things, and would expect that you would respond. I don't want to be the only one working. I want you to work too and understand the process. So you take a stab at it, and if I don't like it, I'll correct it easily, and send it back, and we'll redo it, and we'll talk about it and whatnot. And I guess over the years, I'll offer anybody serious about putting the system in an hour of time. We'll do it by phone, because it's impossible to do in writing. It take us a month with what we could do on the phone in 15 minutes. So, but I'll offer an hour. Okay, and then well, of course, next to the last item is our clubhouse that I just got the award on. So that was kind of neat. And then upcoming, and I don't know what's going to happen, is the one that's targeted for QAX. We're still talking about that. This one is important. Ward is a friend of mine, and he and I have collaborated in creating this book on grounding and bonding. I heartily recommend reading it. It's worth it. It's got a lot of decent material in it, even though I did some of it, so I don't want to be tooting my own horn, but Ward did a great job with it. Okay, and of course, as the club members know, on September 1st of 2021, an EF3 came by and took down both of our towers. So we're in the process. We actually raised the antenna on the new HF tower yesterday. So that was a big, big step. So we're getting there. Okay, questions, comments? We still have a few minutes.
Ron, would it be redundant? So I recently put in UHF, VHF tower. It's a 10-foot, I'm sorry, not tower, antenna. It's a 10-foot comet. It's the bottom of the antenna, of the antenna is just above the top of the peak of my house. And right now, just because I haven't had a chance to finish everything, I have to unplug my radio when I'm not using it to give me that, hopefully, a little bit of extra texture so I can get the coax protection up at the top. What I was planning on doing was putting it literally just at the bottom of the antenna where the custom fabricated bracket is that mounts to the house.
Let me see if I'm not sure I followed. Did you say you were going to put the coax protector at the base of the antenna?
Yes.
Okay.
And then,
Don't do that, please.
okay,
Wasting your money.
okay.
Okay.
So what I do have is the antenna bracket, like I said, is a custom fabrication. It actually is mounted to the inside wall of my attic space. It angles down at the perfect angle to go through the gable vents so that I'm not touching the gable vents, and then it comes out. And from that is where the pipe is mounted for the antenna to be mounted to that. I have a 6-gauge wire going directly to the ground. It doesn't go, it's not actually against the house. It's about 6 to 12 inches away from the house.
Okay, that's good.
Right to a ground rod. That ground rod is connected to 10 feet to the original ground rod that's attached to my utility. And on the other side of that ground rod is the 6 wire that comes out of my office. Takes probably about 30 inches from where my ground bus bar is till it actually comes out from underneath my garage rail, which is not used as a garage. Goes into a seam between the concrete driveway and my apron, runs across 10 feet, comes into the other utility ground so that I don't have anything separate. I don't have any separate grounds. It's all connected somehow.
Okay.
Should I have that antenna grounded at the top from the frame of that bracket? Should that still be grounded down?
Yes, yes. The antenna itself should have a ground.
Okay. So here's where I'm trying to get my head wrapped around. We talk about not wanting to bring the power into the house. I'm trying to understand why it would be bad if I had a coax protector at the top tied into the ground that comes down to a ground rod on the outside of the physical structure, as opposed to having it follow a coax which comes 20 feet in, another 20 feet down, and another 8 feet before it comes back to my station.
Okay.
And having the ground protection in there so that there's like, 40 feet, 45 feet of inside the building.
Gotcha. Okay. It's all about timing. Let's go back to the single point ground picture. This picture will do. Okay. What you want to have happen is you want the coaxial protector to short circuit. You want the AC protector to short circuit at the same time. See, it becomes, you're dealing basically in the nano or tens of nanosecond timing issues. You want them to short, as I say, the coax shorts to the skin of the protector. The AC power shorts to the skin of the protector. Two protectors are mounted on a conductive surface. So therefore, all of the wires, coax and the AC, are all shorted together as a single wire. And the faster that you can get that done, the better off you're going to be. So you don't have any current flow through the radio. So it's all timing. Yeah. But now, if you become really skittish, and I'm not sure that you need to be, but if you become really skittish, you can put a secondary protector up the base of that antenna or where the cable enters the house. Okay. And then if I had my druthers, I would take that number 6 and replace it with an 1.5 or 2-inch wide copper strap, which has its own set of issues from a mounting standpoint and things like that, and an appearance standpoint. But you're dealing with RF, and you want a good, clean, low inductive path. And the simple wide strap is excellent stuff. In fact, inch and a half copper strap actually is slightly less inductive than quad-aught cable, which is, that size. Ever so slightly less inductive, and it's cheaper. Other questions? Yes, sir.
I apologize if I missed this, but on the perimeter ground, I'm presuming as you put the perimeter ground in, that you want to put grounding rods in, all, line it all together, right?
Yes. On the perimeter ground question. You probably can't see them, but there's little dots, little black dots on the perimeter ground. There's one in the corner, one here, one here, one here. So they're about every 16 feet. Yeah.
Is that based upon the soil conductivity in this type?
Based on, some of it is, but this one, the 16-foot rule, or the rule that says it's twice the length. If it's an 8-foot rod, you put them every 16. You can put rods every 6 inches if you so choose. You can't afford it, but you can do it. And it'll be great. Will it be as great as, 150 rods for a 50-foot length? No, it won't be. And in fact, you could probably back out 90% of them and not lose very much. So it becomes a materials optimization or a budget optimization. And so the general rule of thumb is, twice the length of the ground rod that you're sticking in. Can they be closer? Sure. Can they be further apart? Sure. It's all trade-offs, every step of the way. And then, yes, you can also go through a calculation and look at the Siemens centimeters, I think is the right terminology for a cubic centimeter of soil resistance. And you can go through the calculations on that and come up with the optimum. Okay. It's interesting, even on the towers, you see that the rods are kind of still evenly spaced at 16 feet. Or if you look at the energy flow, most of the energy went into the first and second rod, and the time you get to the third rod, it's down by 50%. That means optimally, you could move it in by 50% of the distance and put some more in. But keep it simple. As you look at the overall picture here, though, you find out that there's this particular picture for the clubhouse represents almost 1,000 feet of inch-and-a-half copper strap. That's a lot of copper. That's, yeah. Considering the soil, yes. And about 60 or so ground rods. So I just get a chuckle out of every now and then somebody called me up and said, I put a second ground rod in, and boy, they were so proud of themselves. I cringe, but, it's an education process, and, you walk them through the process of why and how it does, and that's what you get. So, Carl.
I've got some old coaxial lightning protectors that have been in place for a couple of years. Is there a way I can test them to know that they're still doing what they're supposed to do
Yes.
without destroying them?
Oh, yes. I've got a polyphaser impulse suppressor tester. Yeah, I have them. So bring them to one of the meetings, or the board meeting or whatever.
It's not a polyphaser.
Oh, now you want to mix religions. It'll still work. Yeah. Yeah. Now, what I didn't cover, let me just look. I have a minute, don't I? Yeah, I got a minute. I just happen to have a slide of a polyphaser, the best coaxial protector ever made, but I'm biased. You know that. Okay, the antenna is on the left. The receiving equipment is on the right. Okay, frequently the receivers, either have a capacitor input or a RF transformer type input. So it's a path to ground. So that's all that matters. Even the capacitor, initially is going to be a shorted to ground. Okay. In series with the center pin, a very key item is a capacitor. Okay. That's there not because he had extra capacitors laying around and wanted to invent something like this, but the capacitor's there to hold that DC pulse portion of the energy. The RF's going to go through because it's on frequency. But the DC pulse, because of the size of the capacitor, will be held back just a little bit, giving the gas tube a chance to fire. And therefore, you can actually calculate or measure the amount of energy that gets passed into your radio compared to what you stuck in on the input side.
That's an excellent answer, and he didn't ask me to ask that question either. Tough question.
I got a question.
Yes, sir.
I've been installing them for years. What exactly is a gas tube? What does it, I know it short circuits and.
Two plates, as in a capacitor, a ceramic, usually a ceramic housing to hold it together, and a gas of some form inside. Now, it could be a xenon gas, or my brother I know was experimenting with radioactive gases. So it never went anywhere, but I know he had radiation licenses and all that good stuff. Nuclear medicine licenses, I guess what it was. But yeah, it's a gas that it has a known breakdown characteristic. And you can buy gas tubes. I guess sort of the minimum size is about 90 volts, and then they go all the way up into the multiple thousands. And they're somewhat repeatable in that, if it's a 90 volt gas tube, it'll trigger somewhere close to 90 volts most of the time. I mean, there are a spark gap. They are a spark item. So when you excite the gas enough that it flashes over, the voltage goes down from whatever it is down to about 5 or 6 volts. So that's a good thing. It just doesn't trigger as reliably every single time. I mean, it might be 95 volts the next time, or 98 or 110 or 89. But so it'll bounce around a little bit.
So they're more than one-time use. It's just that
Oh yes, oh yes.
the time, the reactionary time should be great over instances.
Yeah, I don't have my slide on reaction times because the devices that are there, there's the gas tube, which is a very capable, very heavy-duty protector. You can easily crowbar 20,000 volts or 20,000 amps through it on a one-shot basis. And then, of course, if it's less, then you get a couple of times to do it. You got the MOV, which is a metal oxide varistor, which is a paste that hardens, and it actually exhibits a threshold that says once the voltage goes above a certain threshold, it effectively short circuits. And they can handle, 10,000 amps. But it gives up its life. I mean, and you get some interesting heat out of them. That's why metal cases are most appropriate. And of course, the commercial power protectors don't come with metal cases. And then there's all kinds of silicon types of devices which are much more fragile and much less current. But they're the fastest acting. They can literally crowbar in a nanosecond or two. The MOVs are sort of second in there, and I don't remember what the number is. And then the gas tubes are the slowest, 20, 30 nanos.
So do they have hybrid ones that do both?
I have seen some funny-looking things, but from a manufacturing standpoint, I look at the price tag and it has a comma in it for a component, so I ignore it. So I can't answer that question well.
What sort of insertion loss do you get from something like this?
Well, I can say on polyphaser protectors are the only ones I've ever.
As an example.
Oh, how nice. Thank you for feeding those words. As an example, a polyphaser, 1/10 of a decibel. So it's not much. Now, some of the others are
Does
probably.
that increase with frequency? Because I saw a capacitor in there.
Well, the power rating, if you're on the transmit side, definitely decreases with frequency. And they are set up for bandpass. So if you take a unit that's designed to handle, say, 2 meters and try to stick HF through it,
So
capacitor's too small.
There's no one product for all bands?
No, no, no. Although if you look at some of the polyphaser products, they do have a DC to speed of light protector. The trouble is, there's no capacitor in there, and I'm not sure what's inside, but it can't be good, although they sell it. So, questions? Thank you, guys.